I was just going to say, I'm real close to finishing grading test 3. I'm confident after class I will finish that off and return that to everyone. Keep in mind there's a couple bonus homeworks due next week, and so there's, in terms of homework, this is the second option, and there's the first thing due tonight. So what's due tonight is not bonus. That's been assigned since last week or before last week. That's substitution stuff. The second, what I'm considering bonus homework, just trying to take it easy on you just a little bit on the end here, is about what we're learning right now. And so it's integration by parts is one of those things. There's one about area and volume, and then there's a third one just about applications. And so I'm just providing those as an opportunity to get some more points. I mentioned these integration by parts and area and volume is usually what you start with in Calc 2. And so we're just kind of finishing up with that introductory level material. It's not going to be on the final. And so I'm providing it as an option to make up some lost ground for past missed homework assignments. And so a couple of people have asked me, like, what if I already had 100 or close to 100 on the homework? Is this going to help me? It's not going to help you. So there's not, like, you can't get more than 100 on the bonus or on the homework. But give them a try, especially one of them is about applications, and you might just be interested to see some of the applications that are out there. So maybe more than anything, it could just show you how you can use this stuff. Anyway, as far as the schedule, you can see that, let's see, we're here on Wednesday. We're going to finish up integration by parts. We'll look at a little bit of application, maybe start that today, finish it up the following Monday, because we don't have class this Friday. So please keep that in mind. How can I make this stand out a little bit? Maybe I'll do it in yellow. All right, we have no class on Friday. It's one of the wellness days. And so we're not meeting. So enjoy. And then next Wednesday, so a week from today, we can do any number of review for the final. We can actually look at some of that on Monday too, if people are interested. And of course, we'll have the final on Friday the 7th. I'd like to make that stand out a little bit more too. Even though I said that yesterday, it seemed like some folks were a little bit confused after class. I got a couple emails about when the final was. So here it is on the 7th, next Friday. It's the first day of the final, or it's in the final exam period. I think it's the second day of the final exam period. I'd like to do it in person. Please let me know ASAP if there's any issues with that. Thoughts about anything before we get started with notes? Questions about anything? I'm trying to think if anything's out there. Just the test is out there, so I don't know if people want to look at some homework, some of the homework that's due tonight.
Yeah, could you help me with a problem from homework tonight? From the homework tonight?
Yeah, what is that one?
It's on number 4.
Can you maybe just read it to me, and I'll just insert a page right here.
Yep. Yes. 1 over x, and then in the denominator it's like x parentheses 1 plus ln of x close parentheses times dx, and then integration goes from e to the fourth to 1, if that makes sense.
Like this?
The other way around, sorry.
E to the 4th is on the top?
Yep.
Yeah. E to the 4th is bigger than 1, so that should go on the top. Yeah. And that looks right. I wrote that down correctly.
Yeah, that's perfect.
Okay. Yeah, so this is sort of kind of like one of the ones that was on the test, and we had one in the homework too, where there was an ln inside of the problem. And so, the whole idea here is, what's u? Well, what are we going to let u be? And remember, the goal here is we want it to be something that when we take the derivative of it with respect to x, we get something else in there in the integral, right? So did you have an idea about what that should be?
Well, I was thinking 1 plus ln of x, because then the derivative would be 0 plus 1 over x, and that's what we have.
Yeah, that's exactly right? Because when you do the derivative, ln turns into 1 over x, and we like that because there's a 1 over x right in the problem. So that looks great. So let's keep going. Maybe maybe you ran into something else later. So the original, maybe when I make the substitution, it's going to be 1 over u du. Does that look right?
Yeah.
Okay. And then what did you have?
I just don't know what to do after that. Like,
Oh, okay. Yeah, so this is one of the specific ln, or I just said it. I was going to say one of the specific
you
integral
have to
rules.
make it into, you have to integrate it, don't you?
You have to integrate it. Yep. What is that? And what do you get when you do that, Janetta?
You got an ln u.
You get ln. Yeah.
Right.
So the integral of 1 over u becomes ln u. And then we had 2 different ways of doing it. You have to plug the points in, right? And so do we put u back in, or do we change the bounds? I don't know if you prefer one, but I like just putting u back in, right? So u was 1 plus ln. So this is kind of strange. You end up with an ln inside an ln, but that's okay. We can do that. Maybe I should move that over because we also need the bounds on there. And then we're going to integrate that from 1 to e to the 4. So how does that look so far?
Okay, that looks good.
And how do you feel about plugging the numbers in? Is that all right? Do you want to? So it would just look like this. You can finish it yourself, but it would be like, first you plug in e to the 4, and then you plug in 1. And ln 1 is 0, actually. So you're going to get, this is just going to equal 0, I think.
All right.
So it's really, I think, just going to end up being this piece. And just to clarify this, right, this is, if this thing is capital F of x over here, then this is f of 4, e to the 4 minus f of 1.
All right, that makes sense. Yeah, thank you.
Sure. Other questions about this one specifically from anyone? Other homework questions or other things you want to look at before we jump into the rest of the notes? All right. So that was substitution. We did have some of that on the last test. There'll be some of that in the final. What we were in the middle of from, I guess it was last Wednesday, so it's been a minute, is what's known as integration by parts. And so it's like substitution that we just looked at, in that it's a method to tackle hard integration problems. And specifically, it's meant to deal with things that came from the product rule. Just like chain rule is how, or substitution is how we undo chain rule, integration by parts is one way to think about it, is undoing a product rule, or at least looking at the form of a product rule. And the top part here is kind of summarizing the method a little bit. The kind of important part, I would say, is the thing I've boxed in twice now, which I'll throw a third box on. Maybe now it's really important, which just kind of summarizes the way that the method works, right? So you're given something that looks like the left-hand side, which I've now circled. You identify u, and I'll remind you how to do that. dv is whatever else is in there. And then you integrate and differentiate to get the right-hand side of the integral. And the idea is the thing on the left that you start with will be impossible to do, but you end up transforming it into something you can do. And so that's, or at least it gets easier, and eventually you can do it. We'll see, sometimes you have to do it twice, is what I'm alluding to a little bit. And so it really comes down to choosing u. It all has to do with u, because dv just ends up being whatever else is not u. And so choosing u is the make or break kind of moment, I'd say, for these problems. And we have this acronym to choose u, right? So this ILATE, I-L-A-T-E, I always think like, I late to class or something. That's how I remember it. ILATE is just tells you, you go through those one at a time to determine what u should be. Because the goal here, and it says here, we talked about this last time, and it says in the descriptions, but where does it say? Taking the derivative of u should make the derivative less nasty, or the integral less nasty. In other words, it should get better when you take the derivative. And so we go through these one at a time, like inverse, log, algebraic, trig, exponential, etc. And whichever one comes up first, that's u. And so just real quick on this first example, x e to the x, we said, what's u? And we said, are there any inverse logs? That's what I stands for. Inverse trig functions? No. Are there any logs? That's what the L stands for. No. Is there an algebraic expression, which really usually means polynomial? Yes, x is an algebraic expression. So that's how we were able to choose the x, right? And then dv was just whatever else there is, which happened to be e to the x. Thoughts about that first step, because that's, if you can't get that, the rest won't follow. And it's really kind of, this acronym really makes it pretty specific what you should be choosing. So if there's anything I can clarify about that, that'd be good. Because after here, it's really just like carrying out steps and following the algorithm. Thoughts about choosing u?
Didn't have what's it called x. The trig one would be cosine or sine or something like that.
Yeah, right. Trig would usually be sine or cosine. So like on this next one, if this 2t wasn't here, this one would be u.
Okay.
It doesn't happen very often because when you take, again, when you take the derivative of u, it should make the problem like simpler. And when you take the derivative of trig functions, they just become other trig functions. And so it doesn't that usually doesn't help. But maybe in extreme circumstances, it works out. I'm trying to think here. Do we have an example of one that uses a trig? No, these are all going to be algebraic, but so we may not see that too much. I'd say you might see that in Calc 2. I mentioned this before, but Calc 2 is pretty heavy on trig, and you do a lot of like substitutions and things like that. So I would think that might be more of a Calc 2 topic. Other thoughts or questions? That was a good one. All right, and then it's just a notation thing, right? If we have u, du just means take the derivative, right? Du means derivative of u. And so if you want du and you have u, you just differentiate it. Similarly, if you have dv and you want v, you undo the derivative. And undoing the derivative means integrating, right? And so hopefully it should be, just looking at like the notation, it should be clear that you get these two things by differentiating and you get these two things by integrating, right? The d means derivative. And then you just plug it into the formula, right? You end up with all the stuff in this formula, u's, v's, dv's, du's. You just plug it in there and you end up with this nicer to deal with integral that we can do. That was sort of where we left off. It was a week ago, so I thought it'd be good to just kind of review that in detail. And so we did a couple definite integrals. All right, take a second and remind yourself, what makes this a definite integral and not indefinite? Remember those two words? What's the difference between the definite and indefinite?
Oh, the bounds?
The bounds, right. So these ones don't have bounds. Excellent. So if we look on this, no bounds, that's why we get the, wherever it is, we get a plus c somewhere, right? You end up with a plus c in your answer because there's no bounds. Now I just want to sort of talk about, well, what happens if we have bounds? How do we actually get area from one of these integration by parts problems? And it's pretty straightforward. It's probably what you would imagine we would do, right? So this is just uv minus the integral of v du is just the formula for integration by parts. And now we're just taking the bounds that were here. Let me make this transparent again. We're taking the bounds that were here, and then we're just putting them here and here as well. But notice the notation, right? This has got the straight line with it, and this is the integral. And so let's just quickly talk about the difference between those two things. This part, when you write a straight line, that just means plug the points in, right? So if you have something that looks like that, function, straight line, integrands, that just means plug in the second one minus plug in the bottom one, right? And so the thing on the left, you just like plug the numbers into, in other words. The thing on the right, you got to do the integration. So that means 1, do the antiderivative, 2, then plug in the points. All right, so just hopefully that was clear, but I just want to be clear about that note. It's a notation thing again, right? It's instructions. It's just knowing what those instructions are telling you to do. And it's the same formula. I'll just make that, I said this in words, but I'll just note that this is the same formula we saw above. It just has bounds now. Thoughts about the notation or anything there? Because we're just going to revisit the problem we just looked at a second ago, this x e to the x one. Right, that was one that we just looked at from above. Except now it's got the number 1 and 6 with it, right? And so instead of just doing some random antiderivative, we're actually going to find the area of this thing. And so I'll just go ahead and write down the work we just did a second ago, but I'm going to fly through it because we just looked at this one moment ago. But maybe it's good to see it one more time in fast motion. So the I stands for inverse trig functions. We don't have any of those. L stands for logarithms, no logarithms. Algebraic expression, yes, there's the x. And so that's how we chose the u part. And then that means whatever's left is dv. Right, so kind of just zoom in over here. This ended up being our u. This ended up being our dv based on the acronym. And what we said was, to get du, you differentiate, right? Here to here, differentiate. If we want to get v, we integrate. And nice thing about e to the x, of course, is it doesn't change. And that's why it's never going to be u, by the way, right? Notice how exponential is like the last option. We'll never let exponential be a u because it doesn't change when you take the derivative. So it's not going to really improve anything. Okay, and then we just write down uv minus the integral v du, but now we have the bounds, right? So I'm just going to slide up here and just show you where I'm copying this from. I'm just going to copy this literal thing we had before, right? I'm going to copy that exact same thing, except now it's going to have the numbers 1 and 6 associated with it. So it looks like uv, but with the bounds, minus the integral of v du. Oops, I forgot to put the bounds on the second integral, right? It's from 1 to 6 now. And just like before, we integrate. You need to integrate this piece, which means find the antiderivative. And it doesn't change, but the difference here is now we don't do a plus c, right? Now we're plugging points in, right? It's a definite integral. And so we're going to do this. Right? E to the x stays the same, and it looks like this. Let me just pause there and let you kind of compare this to the thing from the thing right up top there. Thoughts about that at all? Can I clarify anything there? So then, both these things mean, both of these notations, 1 to 6 with the straight line, just means we're going to plug the points in. Right, and so that looks like this. first plug in 6, then plug in 1. First plug in 6, then plug in 1. And, you know, something kind of interesting thing happens here where the e's to the 1's cancel because you have a minus plus situation. And then you have 6e to the 6 minus 1e to the 6. So that's just 5e to the 6. And so you're welcome to leave it like that. This is a test or something. I would just leave it right like that. If you're curious, this is approximately 2017. Looked at that in a calculator earlier. Make that a little more legible. Just to be, you know, totally clear about what we did there. Where do I have some room? We can slide the graph of this in. The plot of this is actually kind of interesting because you'd think it'd be some strange thing because it's an exponential times x, but it's really just like, it's like a scalar multiple times e to the x. And so it makes e to the x look steeper is the way I think about it. So it looks like kind of like this. It's like a super steep version of e to the x. That's what x e to the x looks like. And we just found the area from 1 to 6. So we just calculated or estimated, sorry, not estimated. We found exactly the area between 1 and 6. Thoughts about that idea? All right, let's look at one more, and then I'm going to give you a chance to try one here. On this next one, we've got ln of x. Let's just draw the graph right up front, just to remind ourselves what we're trying to do here. So we know ln just looks like this. And so we're trying to calculate the area under the curve there from 5 to 10, which seems like it should be pretty easy to do, and it's not terrible, but it is an integration by parts problem, right? It feels like it should just be kind of easy, but it takes a little bit of effort. Because we don't actually have a specific rule for ln. I mean, we can certainly write one down and make one up or whatever, but we can use integration by parts to do it. Now, the tricky thing here is, and maybe you're already trying to think about it, is what do we let u be? And so I'm going to write down ilate again. But if we want u and dv, there's only one thing in there, ln, or is there? Right, so do you see the dilemma a little bit here? Any ideas? I'll give you a hint, but I'm just curious if anyone has an idea.
It would be like x, it's u, and then no.
Good thought. So usually, and not usually, with let me sort of, because I think what you're doing is thinking a little bit about the chain rule.
Yeah.
And substitution. And when in substitution, we always let u be, or not always, but a lot of the time it ends up being the inside thing. Now it's in integration by parts, it's like two things in there and you let u be one of them and dv is the other. So you can't really let it be something inside the other thing, in other words. But that's a good thought. That was a really good thought because we only have one thing. And so I like the idea of like, well, we don't really have one thing. We've got x and ln. So thinking about them separately, but just trying to think about, I'm just trying to say that that's not going to work here because we need it to be like two separate things. And so the sort of trick here that I would describe is ln is really like the number 1 times ln. And so if we think about it like that, there are two things in there and one of them is the number 1. And then if we have the number 1 written in there, then we can use ilate to actually get the correct thing. And there's no inverse logs, inverse trig function, excuse me. I don't know why I keep saying inverse logs. There's no inverse trig function, but there is a log, right? There's an ln. And so that ends up being the u. And then that means dv is the other thing, quote unquote, and the other thing is just the number 1. So I realize that's a little strange, which is why I'm kind of showing it to you. And, you know, newsflash, but upper level math has a lot of like tricks like this. It's like, ooh, do you know this little trick about how it's not just ln in there, it's ln times the number 1. Like, who would really think about that? Well, I think about that because I've seen little tricks like that a lot. So anyway, just sort of the more you see this stuff, the more it comes up over and over again. Anyway, questions about that idea? Because then, you know, once you pick u and then dv follows, you just follow the algorithm and you get the answer. Right, so du, as we differentiate that, that becomes 1 over x. That was the opposite of the question at the start of class, right? We integrated 1 over x to get ln. So we're doing the opposite there. So differentiated. And then we integrate to get v. And when we integrate the number 1, we get x, right? And so some interesting thing happens when we start to do uv minus the integral of v du. How much room do we have here? Let's sneak it in right here. So we're going to do uv minus integral v du. That ends up looking like this. ln x times x, which is not helpful, but you don't have to do anything with that, right? You don't have to integrate. Like, that's kind of an ugly thing is what I mean, but you're just going to plug numbers in there. And then v du ends up being x times 1 over x. And so those two things cancel out, right? Oh, let me throw the integrands on there too. I forgot that. So they're from 5 to 10. Thoughts? Seems okay. So the x and the 1 over x cancel into the number 1. Maybe I should just write that step down, right? It ends up being just integral from 5 to 10 of the number 1. And that's super easy. Right? It just becomes x, and then you plug the numbers in. So I'll write that step down too. Right, you just plug the numbers in at this point. And it ends up being this. Oops, except you plug in the top number first. ln 10 times 10 minus ln 5 times 5 minus 10 minus 5. Did not get an approximate answer for that ahead of time. Not super concerned about it. I mean, you know, if this is a test and a couple people just left it like this on the test, totally fine with me. You know, how well you can plug things into a calculator is not super important. Can I clarify anything there? I would describe that one again as kind of like a trick sort of one, but now that you've seen that trick, maybe you'll see one with an ln in the homework, right? And if you see one with an ln or something like this, maybe you'll have an idea of how it works. Can I clarify something?
Can you explain how you got in the integration? You got 1.
Yeah, so u du ended up being x times 1 over x. And so you have x over x, right? So the x divided by x just cancels into the number 1.
Oh, okay.
Yeah, this just turns into that. Another way to say it, right, when you have a number divided by itself, you get the number 1. Other thoughts? All right, this is your chance to see if it makes sense. So there's another example. It's got a trig function. We haven't done one with the trig function today. Do Did we do one last time with a trig function? We did, sine 2t. Oh, so we did this one previously. So it's your chance to give this one a try. Remind yourself how you did that one last time, except now it's got bounds on it, of course. And so, you know, I won't sort of like let you work on it for 5 minutes or whatever, but let's do it in stages kind of thing. Like I'll write down I late, take a second and think about what u should be. Which one of those things do we have? And then whatever u isn't is dv. Right, take a moment there and think about which of those things we have. And if you need to, you can scroll up or whatever, look at back at that last page, but try to do this one fresh. Thoughts? What do you think you should be? Anyone?
Wait, are we supposed to say what you should be?
Yeah, what do you think you should be?
It should be sine, shouldn't it?
So when we go through these
Well,
things,
actually, it shouldn't be sine because that's trig already. So, and trig should be one of the last ones.
yeah,
And algebra is supposed to be before trig. So 2t.
nice. Nice job thinking through that one. Yeah, I mean, right. So that was a good point. Like trig is one of the last ones, and so very seldom is u going to be a trig function. Oftentimes, if there's a polynomial in there, it's a polynomial. But you know, these other things take precedent. We mentioned before, we're probably not going to see an inverse trig function in here, but we saw a log in the last one, so that happens sometimes. Anyway, so yeah, so u ends up being 2t. And that means dv is the other thing. Oops. Sine. All right, take a second and just think about what is du? How do we get du, right? What's dv, or v, excuse me. All right, how do we do that? It's just starting to come into focus in our mind. What do we do there? Trying to get you to walk through this, and then I'm going to sort of push you along, right? So u is just a function. Du means the derivative of that function. So that means we're going to differentiate. dv means we have a derivative. That means v is the antiderivative then, right? And so that's going to be integrate. Or antiderivative is maybe the other way to say that. All right, so when we differentiate, hopefully we all see we get the number 2. And when we integrate, sine turns into minus cosine. A couple of people I was looking at that today put plus cosine. And I know those are confusing. Don't get me wrong. I struggle with those as well. All right. So take a second and write down the next step, right? We're going to write down u v minus the integral of v du. Go ahead and do that yourself. And then when you pop your head up, maybe it will be the same thing I have. Maybe I'll just wait 1 second. And we're going to have bounds on these too. So maybe I'll throw the bounds on this thing, right? We're going to have from 0 to 10 in this case. Sorry, I just muted a couple of people. I was getting some feedback from, or some static from a couple of people. All right, so that uv ends up being, let's see, u is 2t, v is minus cosine from 0 to 10, and then v du minus cosine, let's see, times 2. How's that look? And I'll just simplify it before I do anything else because there's a bunch of minus signs in there, right? Maybe the minus sign's a little bit tricky because the first minus sign just makes this thing negative. Right, just like a minus 2t now. But then the middle two minus signs, these two things are going to cancel into a plus. And Another way to think about it is you're pulling a -1 out in front of the integral, and then you have a double negative there. You could hold off on that and if you want, because cosine will turn into sine, and you could deal with it later. But I'm just seeing that right now, and so I just thought I would throw it down there. Oh, and then the 2 comes out front as well. And so that's really the kind of thing we want to be thinking about for this one. Look right. You know, these kind of simplification steps are important because if you look at that first thing in blue, it can get a little bit daunting because there's all these negative signs and what's going on. So maybe before we do too much, we can just kind of simplify it a little bit and make it look a little bit easier. Look okay? All right, I'm going to do the integration and plug the points in. So I'm going to still just leave this alone for right now. We could plug them in whenever, but I like doing it all at once. So let's see. Cosine turns into sine from 0 to 10. Wait a second. Derivative of sine is cosine. Cosine is sine. Yeah. And we plug the points in. And it would look like this. -2, I'll do it. -20 cosine 10 minus 0 cosine 0, if you will. And then the other one is 2 sine 10 minus 2 sine 0, which is also 0. That one's not actually that bad. Cosine 10, we might, sine 10, we'll need a calculator for. I'm just going to leave it like that. Looks like we've got some activity outside here. Huh? Sounds like it. How's it look? Integration by parts, love it, hate it. It's not that bad.
Yeah, I like it better than some of the other ones like substitution.
Great. Yeah, a lot of people, for some reason, like substitution better. Now that I'm re-looking at integration by parts for the first time in a little while, it does seem a little bit more straightforward. It's just like, make sure you pick U right, and then everything else should kind of follow. You know, I say that, and then we're about to look at one that's a little bit tricky, so they can get tricky. Thoughts, though? Other thoughts? Okay. So the last one here just sort of points out that, hey, sometimes you actually need to do integration by parts twice, unfortunately. This is where maybe John will get off the wagon of integration by parts. That's where it can be kind of tedious, to say the least. And because, let me actually point out the last one. The reason the last one works so well, and a lot of the previous ones, is because the thing that you let U equal was linear, right, is a power of 1, so that when you took the derivative, there was no variables left. And that was helpful because then when you put it back into the integrand, it was just a constant. And so if it was a bigger power, we'd end up with a t in there, and then we'd be kind of in the same situation we were a second ago. And so that's what happens on this next one. What is it? Can you guys hear me okay? There's like someone mowing right outside my window right now. When we take the derivative of this, that's going to end up being u. It's still going to end up having an x in it. And so we'll have to do integration by parts twice. Is it the end of the world? No. Is it kind of ugly and long? Yes. So I think everyone can follow this. At least I'm not getting a lot of questions. So it seems like maybe folks are sort of getting this so far, but you'll see what happens here. I think about the I late. It's going to be a again. And the a is the quadratic. Right, so our u in this case is this thing. And it's not going to go away, quote unquote, when we take the derivative. Right, and so dv is cosine. You know if that's not okay, but Is that right? So the predicament here is that when we do the du, when we differentiate this, we still have x's. This thing is going to be a problem, the x, because when we stick it back in, we're going to still have trig function times x, and so we'll have to do it a second time. Just kind of looking ahead at what's going to happen, right? And then we integrate the second part, of course, and we get sine. Right, so when we do uv minus integral v du, here's what it looks like, and you'll see that there's an issue here. So let's see here, uv minus integral v du. And the spot that we're in right now looks very, very similar to the spot we started in. Right? It was like trig function times polynomial. It's just slightly better because at least it's not a quadratic, right? It's not a power of 2, it's just a power of 1. And so we can imagine when we do integration by parts again, on that piece, the linear function is going to go away, or it's going to become a constant at least, and then it'll work the second time. So that's the sort of thing that I am talking about.
So I kind of see that, but like when you originally have 2x squared plus 3x, why won't that like work?
Because when we differentiated it here, let me do another color so it stands out. When we differentiated it here, it still had an x in it. And so when we ended up sticking it in, it still had an x. Or I think the better thing to do is to compare it to the last one, or some of the previous ones. Like in this case, when we differentiate it, we just get a constant. And so then when we stick it back in, it's nice, right? It's just a constant multiple. Same thing with like this one, right? When we differentiate it, we just got a constant. And so when we stuck it back in, it was just a constant multiple. So if it's not just a linear function, i.e. power of 1, like this one was a linear function too, which made it nice, then we're going to have to do it twice. Or maybe another question is, what if this was like 2x to the 4th, ... How would that change things? John or anyone else?
Would you have to do it like more than twice, like 3-4 times, or I don't know?
Yeah, we'd probably, so, you know, this one meant we did it 2 times. This means we'd probably have to do it 4 times. Would you expect to see a problem like that? I hope not. I mean, you know, not on like a homework or something, but just practically speaking, that's what it looks like. And every time, and you'll see it in a second, every time we get another integration by parts. So it's like, it just gets bigger and bigger and bigger. It's kind of like, you know, we're undoing the product rule here, right? So remember when we did product rules inside product rules, and we had like 1 became 2, and then if you had a product rule in there, it became 4, and then if you had another one, it became 8, and it just kept being crazy. Anyway, other thoughts?
Wait, so basically you're going to have to just do it again inside of the problem or something?
Yeah, because right, the next step here is to do this integral, and if we want to do that integral, it happens to be an integration by parts question, and so we did integration by parts, but now we're looking at this and we're like, oh, we're still in that same situation, and we're just going to do it a second time. And it's very similar, right? Because u is the 4x plus 3. And so that means du is just 4. So that's going to be good because that's just going to be a constant multiple. And then that means dv is the other thing, which is sine. And so v is minus cosine. Cosine. I think that's right. And so you can see I've left some room here because I knew this one was going to be kind of long. So this part just kind of copies down, right? This part here is just going to, we didn't change anything there. But the next piece becomes the integration by parts. So it's going to be like u v minus integral v du. And, you know, again, this is a definite integral. And so if it was an, sorry, it's an indefinite integral. If it was a definite integral with bounds, it would be even crazier because then we have to plug stuff into each one of these things. Excuse me. All right, just going to pause there. I think I'm going to end with this one too. So I'm going to kind of slowly do this, see if anyone has any questions here. And so I guess the point here is notice how this thing that we ended up with here, cosine 4x, or sorry, cosine x times 4, that's a super easy thing to do, right? It's a constant multiple times the integral. I'll simplify it just to kind of show you that, but writing the next line now. Okay, I'm going to just, yeah, this is where it gets a little confusing. I'm going to distribute this negative sign. So it's going to make this thing positive, and then it's going to make this thing negative. So it's going to look like this. Let me know if this looks okay.
You were able to do that because there's like a hypothetical one there. Is that
The second, so yeah, this is where algebra, you know, like having an understanding or a strong understanding of algebra can be really helpful. So it's like this negative sign was subtracting this whole thing. And so that's the same negative sign. It's just that the inside piece became a different, bigger thing, but the whole thing is still being subtracted. Right, so like when I did the integral, it's like, okay, but this whole thing still being, that's why I was trying to be careful with this, like doing the brackets.
all right? That's clear.
And then, you know, just to make it more clear for other people who are not a little confused, it's like you had a negative here and a negative here. So that's why it became positive. And then the third one, it's like you have 3 negatives. You have these 2 negatives, which make it a plus. But then this one makes it negative again. That's why this one is negative. It's like -1 times -1 times -1. So that's a bunch of algebra, mostly, not mostly, that is just algebra. Let me know if it's confusing. I'm happy to clarify it, but you know, if this is a test, I wouldn't do something that's, I hope I wouldn't do something that confusing. All right, then we just integrate that last part and we're done. We got to throw the plus C on though. Don't forget about the plus C. We did all this work. We want to have the plus C. See, so cosine turns into sine plus C. Whew, that one's a little bit of a doozy, but if you can follow that, kind of understand why we need to do it twice, I think you're in great shape.
So, like, since we don't have bounds on this one, and like this one has the plus C.
Yep. Yeah, that's exactly right. I thought that was I thought you were making a statement. Yes, because there's no bounds on this one, that's what gives it the plus C over here. It's finding the family of antiderivatives, not area. Other thoughts? Can you guys tell I'm not home?
I noticed that when you like went to look out the window.
I just realized that. I didn't even know.
I was trying to play around with that. I'm away, and I didn't want to think about like where I was sitting, so I just took a picture at home and tried to make it my background, but it doesn't work very well. Yeah, and there's some picture behind me that keeps like popping out on the wall. Works pretty good. All right, well, I'm going to stop there. This can be a short class. We're right at the end of the notes here. I don't mean to belabor you guys. I appreciate you sticking with me this long. So happy to answer some questions though. Or Josh didn't notice I fooled him. Questions about this one or other ones?
I'd like to ask what we should study for the finals.
Yeah, so it's going to be a combination of the first 3 tests. So if we go back to the class note or the semester schedule here, what I have mentioned is the final exam topics are going to be a combination of the test 1, 2, and 3 topics. So I'm not going to tack these extra things on here that we're kind of doing right at the end. I feel like the first 3 tests is way more than enough material. And it also means that you don't have to like a topic sheet or sort of do anything extra. So in other words, all the material, all the review material, all the topics are up there already. All the practice problems, it's all stuff you have, and you should use test 1, 2, and 3 to study. So there's, sometimes people get to this point and you're like, can't you give us some more practice problems? I feel like if you can do all the problems we have out there, you're good. There's a lot of problems out there. But just to direct you a little further, test 1, 2, and 3 are definitely things you should know how to do. The quizzes, right? Because I write those. I don't write necessarily the online homework problems. I write the homework or the tests and the quizzes. So like those are the problems you should start with first. Other thoughts or questions? Keep them coming.
So no class Friday, and then Monday we'll be finishing up the notes, and then Wednesday is just like the review, and then is that?
Yep. Yeah, this is all messy now, but yeah. So I'll see you guys. We have 2 more classes. We have Monday, it'll be another short class, just looking at the notes. There's like a couple pages that I like to finish on as a useful kind of interesting thing, I think. Anyway, but there'll also be time for review is what I'm trying to say. So this is going to be probably a shorter class on Monday. And if you want to talk about homework questions, review questions, the final will be 4 days away at that point. So that would be, you should, be studying a little bit. I just saw Tommy's question. Yeah, there's no integration by parts in the final.
And is there any way that we could get extra credit, or is that too late?
Thoughts about that, anyone? I mentioned an extra credit assignment at the beginning here.
Well, if we did all the homework this semester and we did that we can't get like over 100, right?
Not on the homework. I don't know. I guess maybe if you did that homework, I would give you some bonus points on something else. How's that? So I guess I'll say it again on Monday, but said this a bunch of times already. There's optional homework due next week that you can apply as bonus points. I had previously said you can't get more than 100% on homework, and I still like to stick with that. I think if you have 100 on the homework, you got 100 on the homework. But I could imagine how someone has 100 on the homework, but not 100 on quizzes or tests, obviously, right? So I'm not going to just like add points to your homework though. So, what I'm going to do for these points, like if you get, there's 14 possible problems, I just erased it. There's 14 bonus problems. Every one you get correct, I'll add into homework problems. If they're quiz, if you want me to add it into quiz, maybe like, I don't know, 1 every 3, so that'd be up to like 4 or 5 points. So here's the ratio, 1 to 1 for homework. I'll do 3-1 on quizzes.
That's generous.
And yeah, say that again, John.
I said that's generous.
Yes, that is generous. I don't know if you're serious or not, but I think it is.
No, I am.
And I don't know, Tess. It's hard to say. Maybe 4-1. That's still pretty good. You get like 3 or 4
You
test
missed
points.
Josh's offer.
2-1 final offer. 2-1 seems a little bit much. 4-1, maybe 3-1. I would almost take it on a case-by-case basis. If someone needs points, I'll be a little more generous. If you're like getting an A- and you're looking for that A, then I'm gonna ask you to do well in the final, probably. I'm trying to help within reason here.
Well, then thanks. You've been a wonderful professor.
Oh,
Just letting you
wow.
know.
You're just gunning for that extra credit. There we go. Keep it coming. No, I appreciate that. Any other thoughts? I'm also going to drop the lowest. I usually drop the lowest 10% of homeworks and quizzes, although I give a different amount of quiz this semester. How many quizzes I get? I think I still gave like 10 quizzes, didn't I? So I'll drop the lowest 10%. So I think that means 1 quiz and like 3 homeworks or something like that. Yeah, I give 10 quizzes, so I'll drop the lowest quiz for sure. Anything else? Alrighty. I'll see you guys on Monday. Have a great weekend.
Thank you.
You too. Bye.
Bye.
So test later today. Test scores.
Oh yeah. Yep. I'm gonna go look on that right now.
Alrighty. Thank you again. Have a great day. See you
Take care.
Monday.
Bye. Give me 1 second, Gregor. I'm gonna talk to someone. All right, you want to do this thing? Okay.
I'm ready.
Gonna try sending you through the chat, but I seem to remember that didn't work for you before. So let me see if that works.
Yeah.
I just sent it.
Nope.
All right, I'm emailing.
Cool.
All right, coming through.
I've got it.
Great. Let me know if you have any questions. I'll be around working here, like on the computer.